Welcome to Deep Science Sleep. Take a deep breath in and let it out slowly. Feel yourself sinking deeper into your bed, your pillow cradling your head perfectly, the blankets wrapping around you like a gentle embrace. Tonight, you're going to drift off to sleep while learning about one of Earth's most peaceful processes. Something so slow and gentle that you could never feel it happening, yet so powerful that it has shaped every mountain, every ocean, every continent on our planet. Imagine yourself floating high above the Earth, weightless and calm, looking down at the continents and oceans from a peaceful vantage point high in space. From here, everything appears still, serene, unchanging. The clouds drift slowly across the blue marble below you. But beneath this tranquil surface, there's a story unfolding so slowly, so gently, that you could never perceive it in a single human lifetime. It's the story of continents drifting across the face of our world, of mountains rising grain by grain, of ocean floors spreading apart at the pace of growing fingernails. Tonight, we're going to explore the most soothing science on Earth, the gentle, perpetual dance of tectonic plates that has been choreographing our planet's surface for billions of years. Let the rhythm of these ancient, patient processes lull you into the deepest, most restful sleep. Close your eyes, settle in, and let's begin this journey into the peaceful world beneath our feet. The discovery of continental movement. Our story begins over a century ago, with a German scientist named Alfred Wegener who noticed something peculiar while looking at a world map. It was a simple observation, the kind that seems obvious once someone points it out to you, like recognizing a face in the clouds. He noticed that the coastlines of South America and Africa seemed to fit together like pieces of a jigsaw puzzle. The eastern bulge of South America appeared to nestle perfectly into the western curve of Africa, as if they had once been joined and had somehow drifted apart. Wegener wasn't the first person to notice this curious similarity. As early as the 1600s, mapmakers and natural philosophers had remarked on the apparent fit between continents across the Atlantic Ocean. But Wegener was the first to take this observation seriously and pursue it scientifically. In 1912, he proposed a revolutionary idea that he called continental drift. He suggested that all the continents had once been joined together in a single massive supercontinent, which he named Pangaea, meaning all Earth in Greek. Imagine, if you will, a world 250 million years ago. All the land on Earth was gathered together in one enormous landmass, surrounded by a vast, planet-wide ocean called Panthalassa. There were no Atlantic or Indian Oceans separating the continents. South America and Africa were pressed together. North America nestled against Europe and North Africa. India was tucked against Antarctica, which itself was connected to Australia and South America. All the continents we know today were part of this single, unified landmass. Wegener didn't just rely on the shapes of coastlines to support his theory. He gathered evidence from multiple scientific disciplines, weaving together observations from geology, paleontology, and climatology. He found that certain rock formations and mountain ranges seemed to continue from one continent to another. The Appalachian Mountains in North America, for instance, appeared to be part of the same ancient mountain chain as the Scottish Highlands and the mountains of Scandinavia. When you mentally pushed the continents back together, these mountain ranges lined up perfectly, like a torn photograph being reassembled. The fossil evidence was even more compelling. Wegener discovered that identical fossils of plants and animals appeared on continents that were now separated by thousands of miles of ocean. There was Mesosaurus, a small freshwater reptile whose fossils were found only in South America and southern Africa. This creature couldn't have swum across the vast Atlantic Ocean, and it seemed highly unlikely that identical species would have evolved independently on two separate continents. The most logical explanation was that these continents had once been connected, allowing Mesosaurus to live across what was then a single landmass. There was also Glossopteris, a seed fern whose fossilized remains appeared in South America, Africa, India, Antarctica, and Australia. These widespread identical fossils made sense only if these continents had once been joined, allowing the plant to spread across the unified landmass before the continents drifted apart. Similarly, fossils of Lystrosaurus, a mammal-like reptile, were found in Africa, India, and Antarctica, three continents now separated by oceans but once connected in Pangaea. Wegener also pointed to ancient climate evidence preserved in rocks. He found signs of ancient glaciation, scratches and grooves carved into bedrock by moving ice sheets, in places that are now tropical. In Africa, South America, India, and Australia, he discovered evidence that these regions had once been covered by massive ice sheets, even though they now sit near the equator where ice sheets cannot form. When Wegener reconstructed Pangaea and positioned these continents near the South Pole, the glacial evidence suddenly made perfect sense. Despite this compelling evidence, Wegener's ideas were met with skepticism and outright hostility from much of the scientific community. The problem wasn't with his evidence, which many scientists found intriguing. The problem was that Wegener couldn't explain how continents could possibly move. What force could be powerful enough to push massive continents through the solid rock of the ocean floor? Wegener suggested that continents plowed through oceanic crust like ships through ice, but physicists calculated that this was impossible. The forces required would be astronomical, and there was no known mechanism that could provide such power. Many scientists dismissed continental drift as an interesting but ultimately flawed idea. Some were quite harsh in their criticism. One prominent geologist described Wegener's theory as utter rot and suggested that anyone who believed in it was either gullible or a fool. The opposition wasn't entirely unreasonable from a scientific perspective. Wegener was asking the scientific community to overturn fundamental assumptions about the Earth based on circumstantial evidence and without a clear mechanism. In science, extraordinary claims require extraordinary evidence, and many felt Wegener hadn't met that burden of proof. The debate over continental drift revealed something important about how science works. It's not enough to simply have an interesting idea or to point out intriguing patterns. You need to provide a mechanism, a way of explaining not just what happens but how and why it happens. Wegener could show that continents appeared to fit together and that fossil and rock distributions made sense if continents had once been joined. But he couldn't explain what force could possibly move entire continents across the Earth's surface. Wegener proposed several mechanisms, none of which proved satisfactory. He suggested that centrifugal force from Earth's rotation might push continents toward the equator, but calculations showed this force was far too weak. He suggested tidal forces from the moon and sun might drag continents westward, but again, the forces were inadequate. Without a plausible mechanism, continental drift remained, in the eyes of many scientists, an interesting speculation rather than an established theory. Wegener defended his ideas throughout his life, giving lectures, writing papers, and revising his book through multiple editions. He remained convinced that continental drift was real, even as the scientific establishment largely rejected his ideas. He died in 1930 during an expedition to Greenland, still convinced he was right but unable to prove the mechanism behind continental drift. His body was never recovered. He's presumably still buried somewhere in the Greenland ice sheet, that vast remnant of the Ice Age he had studied in connection with his continental drift theory. For decades after his death, Wegener's work was largely forgotten or dismissed as an interesting but failed attempt to explain geological patterns. His ideas persisted on the margins of geology, kept alive by a few advocates who believed he was onto something important, but mainstream geology moved in other directions. It would take new evidence from an unexpected source, the floor of the deep ocean, to vindicate Wegener's vision and transform our understanding of how the Earth works. For decades after Wegener's death, his theory remained on the fringes of geology, considered by most scientists to be an intriguing but ultimately incorrect hypothesis. The continents, conventional wisdom held, were fixed in place and had been since the Earth formed. The idea that they could drift across the planet's surface seemed too fantastic to be true. But Wegener had planted a seed, and over the following decades, that seed would slowly germinate as new evidence accumulated. Evidence that would eventually vindicate his vision and revolutionize our understanding of how the Earth works. What Wegener couldn't have known, what no one in his time could have known, was that continents don't plow through ocean floors. Instead, both continents and ocean floors ride atop massive plates of rock that float on the semi-molten layer beneath. The continents aren't moving through the ocean crust but rather with it, as parts of larger tectonic plates. This revelation would come decades later, transforming Wegener's continental drift into the more comprehensive theory of plate tectonics, a theory that would explain not just how continents move, but why they move, driven by forces deep within the Earth that Wegener could never have imagined. Understanding Earth's layers and the engine within. To understand how tectonic plates move, we need to journey deep into the Earth, descending through layers of rock and metal until we reach the planet's blazing heart. Close your eyes and imagine yourself sinking down through the ground beneath you, passing through soil and stone, diving deeper and deeper into our planet's interior. What you'd discover is that Earth is structured like a soft-boiled egg, with distinct layers that differ in composition, temperature, and physical properties. The outermost layer, the one we walk on every day, is called the crust. This is the thin, solid shell of rock that forms the continents and ocean floors. The crust is not uniform. It comes in two distinct types with very different characteristics. Continental crust is typically 30 to 40 kilometers thick, though it can reach up to 70 kilometers beneath major mountain ranges like the Himalayas or the Andes. It's composed primarily of granite and other silica-rich rocks that are relatively light in color and low in density. Continental crust is ancient. Some rocks in continental crust are nearly 4 billion years old, dating back almost to the formation of Earth itself. Oceanic crust, by contrast, is much thinner, averaging only 5 to 10 kilometers in thickness. It's composed primarily of basalt, a dark, dense volcanic rock. Oceanic crust is also much younger than continental crust. The oldest oceanic crust currently on Earth's surface is only about 200 million years old. This is because oceanic crust is constantly being created at mid-ocean ridges and destroyed at subduction zones, recycled through the mantle in a way that continental crust is not. If the Earth were the size of an apple, the crust would be thinner than the apple's skin, a delicate shell surrounding the vast bulk of the planet's interior. Yet this thin shell is where we live, where all of life as we know it exists, where all of human history has played out. It's this thin, brittle layer that's broken into the tectonic plates we'll discuss throughout this journey. Fractured like an eggshell but still functional, still protecting the hot interior beneath. Beneath the crust lies the mantle, a much thicker layer of hot, dense rock that extends down to a depth of about 2,900 kilometers. The mantle makes up approximately 84% of Earth's total volume. Near the top of the mantle, just below the crust, is a region called the asthenosphere, which extends from about 100 to 200 kilometers deep down to about 650 kilometers. The asthenosphere is particularly important for plate tectonics because this rock is hot enough and under enough pressure that it behaves in a plastic or ductile manner. It's not liquid, mind you, but it can flow very slowly over geological timescales, like extremely thick honey or hot taffy. The upper part of the mantle, along with the crust, forms what we call the lithosphere. This is the rigid outer shell of the Earth, the part that's broken into tectonic plates. The lithosphere is about 100 kilometers thick on average, though it can vary significantly. It floats, in a sense, on the more plastic asthenosphere beneath it. This is the key to plate tectonics. Rigid plates of lithosphere sliding and shifting atop the flowing asthenosphere. Below the asthenosphere, the rest of the mantle becomes increasingly dense and hot, but it's also under such tremendous pressure that it behaves as a solid despite temperatures that would melt rock at the surface. The mantle's temperature increases with depth, from about 500 degrees Celsius just below the crust to approximately 4,000 degrees Celsius at the boundary with the outer core. At about 2,900 kilometers deep, we reach the outer core. This is a layer of liquid iron and nickel, heated to temperatures between 4,000 and 6,000 degrees Celsius. The outer core is about 2,200 kilometers thick, and it's in constant motion. The swirling, convecting liquid metal in the outer core generates Earth's magnetic field through a process called the geodynamo. This magnetic field extends far into space and protects our planet from harmful solar radiation. But that's a story for another night. Finally, at the very center of our planet, about 5,100 kilometers below the surface, lies the inner core. This is a solid sphere of iron and nickel about 1,200 kilometers in radius. Despite temperatures that reach an astounding 5,000 to 7,000 degrees Celsius, hot enough to match the surface of the sun, the inner core remains solid because it's under such immense pressure. The weight of all the rock and metal above it squeezes the inner core so tightly that the atoms can't spread apart to form a liquid. Now, the question that puzzled scientists for decades after Wegener proposed continental drift was this: what makes the plates move? What engine could be powerful enough to push continents across the face of the Earth? The answer lies in the heat of Earth's interior and a process called mantle convection. The Earth contains an enormous amount of heat. Some of this heat is primordial, left over from when the planet formed 4.5 billion years ago through the violent collision and accretion of smaller bodies. When these countless chunks of rock and metal smash together, their kinetic energy converted to heat, melting the early Earth into a ball of molten rock and metal. Some of that original heat is still trapped deep within our planet, slowly radiating outward. But the Earth also generates new heat through radioactive decay. The mantle and crust contain radioactive elements like uranium, thorium, and potassium. These unstable atoms gradually break down over millions and billions of years, and as they decay, they release energy in the form of heat. This radioactive decay has been warming the Earth's interior for billions of years and will continue to do so for billions more. This heat has to go somewhere. Like any hot object, the Earth is constantly losing heat to the cold vacuum of space. Heat flows from the hot interior toward the cooler surface, where it radiates away into space. This cooling process has been ongoing since the Earth formed, and it will continue for billions of years to come. In fact, the Earth is very slowly cooling over geological time, though the process is so gradual that it will take billions of years for the interior to cool significantly. But rock is an excellent insulator, so this heat can't simply conduct through the mantle the way heat conducts through a metal rod. If the Earth relied solely on conduction to move heat from the core to the surface, the heat would flow too slowly, and the interior would heat up until the entire planet melted. Instead, the heat escapes primarily through convection, a much more efficient heat transport mechanism. Convection is a process you can observe in a pot of soup on the stove, or in a lava lamp, or in the way thunderclouds form on a hot summer day. Hot soup at the bottom of the pot becomes less dense because it expands as it's heated, and this less dense hot soup rises toward the surface. Cooler soup at the surface becomes denser as it cools, and it sinks toward the bottom, where it's heated again, and the cycle continues. This creates a circulation pattern, with hot material rising and cool material sinking, efficiently transporting heat from the heat source to the surface where it can be lost to the environment. The same process occurs in the Earth's mantle, though infinitely slower than in a pot of soup. Hot rock in the deep mantle, heated by the Earth's core and by radioactive decay, slowly becomes less dense and rises toward the surface. This rise takes millions of years. The rock moves at only a few centimeters per year. As it rises, the rock gradually cools, transferring its heat to the surrounding material. Eventually, it reaches the base of the lithosphere, where it can rise no further because the lithosphere is rigid and blocks its ascent. The rock then begins to move horizontally, flowing beneath the lithosphere, dragging the overlying tectonic plates along with it. Meanwhile, elsewhere in the mantle, cooler rock near the surface becomes denser and sinks back down into the deep mantle. This sinking occurs primarily at subduction zones, where old oceanic lithosphere descends into the mantle. The descending lithosphere is cooler and denser than the surrounding mantle, so it sinks under its own weight, pulling the rest of the plate behind it. This sinking lithosphere is one of the main driving forces of plate tectonics, perhaps even more important than the push from rising mantle currents at mid-ocean ridges. This creates vast, slow-moving circulation patterns in the mantle, giant convection cells that cycle rock between the deep mantle and the base of the lithosphere. These convection currents move extraordinarily slowly, at rates of only a few centimeters per year. To put this in perspective, your fingernails grow faster than mantle rock circulates. A snail moves faster than mantle convection. Yet this sluggish circulation is powerful enough to move entire continents, to open and close ocean basins, to raise mountain ranges kilometers high. The pattern of mantle convection is complex and not fully understood, even today. It's not simply a matter of hot rock rising and cold rock sinking in neat, orderly cells. The mantle is not homogeneous. It contains variations in temperature, composition, and water content that affect how it flows. There may be plumes of hot rock rising from deep in the mantle, creating volcanic hotspots like Hawaii or Iceland. There may be ancient fragments of subducted oceanic crust accumulated at the boundary between the mantle and the core, influencing the pattern of convection. Scientists are still working to understand the details of how mantle convection operates and how it has evolved over Earth's history. These convection currents move extraordinarily slowly, at rates of only a few centimeters per year. To put this in perspective, your fingernails grow faster than mantle rock circulates. But over millions of years, these slow currents have profound effects. The moving mantle drags the overlying tectonic plates along with it, pulling them in different directions. In some places, rising currents push plates apart. In other places, sinking currents pull plates together. This is the engine that drives plate tectonics. The slow, patient circulation of heat through the mantle, powered by Earth's internal furnace. At mid-ocean ridges, where plates are pulling apart, hot mantle rock rises to fill the gap. As this hot rock nears the surface, the pressure on it decreases, causing it to partially melt and form new magma. This magma erupts onto the ocean floor, cools, and solidifies into new oceanic crust, which then slowly moves away from the ridge as more new crust forms behind it. This process, called seafloor spreading, continuously creates new lithosphere at a rate of a few centimeters per year. At subduction zones, where plates converge, old oceanic lithosphere sinks back into the mantle. The cool, dense oceanic plate descends into the hot mantle, where it's gradually reabsorbed and recycled. In this way, the Earth's surface is constantly renewing itself, with new crust forming at mid-ocean ridges and old crust being destroyed at subduction zones. The entire ocean floor is replaced roughly every 200 million years through this cycle of creation and destruction. This slow, steady recycling is one of the most peaceful and constant processes on Earth. Right now, beneath the oceans, new crust is quietly forming, cooling, and spreading outward. At the same time, old crust is gently sinking back into the mantle, melting and mixing back into the rock from which it came. This process has been continuing for at least 3 billion years, perhaps longer, cycling and recycling the Earth's surface in an endless, patient rhythm that will continue for billions of years into the future. The heat engine that drives this process is so vast and so powerful that it's almost incomprehensible. The amount of energy involved in moving entire continents, in creating and destroying ocean floors, in raising mountain ranges kilometers into the sky, is staggering. Yet it all happens so slowly, so gradually, that we never feel it. The continents drift at about the same rate your fingernails grow, a few centimeters per year. Mountains rise by a few millimeters annually. Ocean floors spread at rates measured in the width of a finger per year. This is the beautiful paradox of plate tectonics. The forces involved are enormous beyond imagining, yet they manifest as the gentlest, slowest changes imaginable. The Earth is constantly transforming itself, endlessly sculpting and reshaping its surface, but it does so with infinite patience, over timescales so vast that human lifetimes are like single heartbeats in comparison. The birth of plate tectonic theory. While Alfred Wegener had correctly identified that continents move, the mechanism remained a mystery for decades after his death. The revolution that would vindicate Wegener's vision and birth the modern theory of plate tectonics began in the 1950s and 1960s, driven by new technology and observations of the ocean floor. During and after World War II, significant advances were made in sonar technology, originally developed for detecting submarines. Scientists began using this technology to map the ocean floor in unprecedented detail. What they discovered was astonishing. Far from being flat and featureless, the ocean floor was revealed to be a landscape as dramatic and varied as any continent, with towering mountain ranges, deep valleys, and vast plains. One of the most significant discoveries was the mid-ocean ridge system, a continuous chain of underwater mountains that winds through all the world's oceans like the seam on a baseball. This submarine mountain range is the longest mountain chain on Earth, extending for over 65,000 kilometers. The Mid-Atlantic Ridge, the best-known segment of this system, runs down the center of the Atlantic Ocean, roughly following the curves of the continental coastlines on either side. At the crest of these mid-ocean ridges, scientists discovered something peculiar: a deep central valley or rift where volcanic activity was occurring. Underwater volcanoes were erupting along the ridges, creating new oceanic crust. This observation led to one of the key insights of plate tectonics. In 1960, a geologist named Harry Hess proposed a theory he called seafloor spreading. Hess suggested that new ocean floor was being created at mid-ocean ridges through volcanic activity, and this new crust was then spreading away from the ridge in both directions, like a conveyor belt. This would push the continents apart, providing the mechanism for continental drift that Wegener had been unable to identify. Hess's theory was initially speculative, but it soon received dramatic confirmation from an unexpected source: Earth's magnetic field. Scientists had known for some time that the Earth's magnetic field occasionally reverses, with the north and south magnetic poles switching places. These reversals happen irregularly, sometimes after hundreds of thousands of years, sometimes after millions of years. The exact timing and causes of these reversals are still not fully understood, but the geological record clearly shows they occur. When volcanic rock cools and solidifies, magnetic minerals within the rock align themselves with Earth's magnetic field at that time, like tiny compass needles frozen in place. This creates a permanent record of the magnetic field's direction when the rock formed. In the early 1960s, scientists began measuring the magnetic properties of rocks on the ocean floor, and they made an extraordinary discovery. On either side of mid-ocean ridges, the ocean floor displayed a pattern of magnetic stripes. Some stripes had magnetic minerals aligned with the current magnetic field, while others had minerals aligned in the opposite direction, indicating they formed during periods when the magnetic field was reversed. Most remarkably, these stripes were symmetrical on either side of the ridge. The pattern of stripes on one side of the ridge was a mirror image of the pattern on the other side. This magnetic striping provided smoking gun evidence for seafloor spreading. As new crust formed at the mid-ocean ridge, it recorded the magnetic field direction at that time. As the seafloor spread away from the ridge, it carried this magnetic record with it. When the magnetic field reversed, newly forming crust would record the reversed field, creating a new stripe. The symmetric pattern on both sides of the ridge proved that the ocean floor was indeed spreading away from the ridge in both directions, exactly as Hess had proposed. By measuring the width of these magnetic stripes and dating the timing of magnetic reversals using other geological methods, scientists could calculate how fast the ocean floor was spreading. They found that spreading rates varied from about 2 centimeters per year at slow-spreading ridges to about 20 centimeters per year at fast-spreading ridges. These rates might seem trivial, but over millions of years, they add up to thousands of kilometers of movement. The magnetic striping of the ocean floor was one of those rare pieces of evidence that was simultaneously simple and profound. Once you understood what you were looking at, the pattern was clear and undeniable. The ocean floor was spreading away from mid-ocean ridges, creating new crust as it went, and recording the reversals of Earth's magnetic field in the process. It was like a tape recorder, continuously recording the magnetic field and preserving it in rock. This discovery transformed seafloor, spreading from an interesting hypothesis into an established fact. Scientists could now measure how fast the ocean floor was spreading. They could calculate when different parts of the ocean floor had formed, and they could trace the history of ocean basins backward in time. The entire Atlantic Ocean, from its birth as a narrow rift to its current width of 6,000 kilometers, could be reconstructed in detail based on the magnetic stripes on its floor. But this elegant evidence also raised new questions. If new ocean floor was constantly being created at mid-ocean ridges, spreading outward at measurable rates, and if the Earth wasn't growing larger, then where was all this new crust going? The ocean basins should be overflowing with crust. The continents should be drowning under rising seas, unless old crust was being destroyed somewhere at roughly the same rate that new crust was being created. The discovery of seafloor spreading solved half the puzzle of continental drift. It explained how new crust was created and how continents could be pushed apart. But this raised a new question. If new crust was constantly being created at mid-ocean ridges, why wasn't the Earth getting bigger? Where was the old crust going? The answer came from studying the deep ocean trenches, particularly those around the Pacific Ocean. Scientists discovered that these trenches marked places where oceanic crust was being pulled back down into the mantle in a process called subduction. At subduction zones, one tectonic plate slides beneath another, descending into the hot mantle where it's eventually reabsorbed. This process destroys old oceanic crust at roughly the same rate that new crust is created at mid-ocean ridges, keeping the Earth's size constant. These discoveries came together in the mid-1960s to form the theory of plate tectonics. The Earth's lithosphere, scientists realized, is broken into about a dozen major plates and several smaller ones. These plates are in constant motion, driven by mantle convection. At divergent boundaries, plates pull apart and new crust forms. At convergent boundaries, plates collide and one is subducted beneath the other. At transform boundaries, plates slide past each other horizontally. The theory of plate tectonics represented one of the greatest scientific revolutions of the 20th century. It provided a unifying framework that explained a vast range of geological phenomena. Why earthquakes and volcanoes occur where they do, how mountain ranges form, why ocean basins have the shapes they do, how continents have moved over time, and much more. Wegener's vision of drifting continents was vindicated. but in a more sophisticated and comprehensive way than he had imagined. The acceptance of plate tectonics wasn't immediate. Many older geologists trained in the idea of a static Earth were reluctant to abandon their long-held beliefs. But the evidence was overwhelming, and by the 1970s, plate tectonics had become the central organizing principle of geology, as fundamental to that science as evolution is to biology or the atomic theory is to chemistry. What's remarkable about this scientific revolution is how recent it is. The theory of plate tectonics is younger than many people alive today. For most of human history, and indeed for most of the history of geology as a science, we had no idea that the continents moved or that the Earth's surface was in constant motion. It's only in the last 60 years or so that we've come to understand the dynamic nature of our planet. This understanding has profound implications. It means that the world map we see today is just a temporary snapshot of a planet in constant flux. The Atlantic Ocean is about 180 million years old, and it's still growing wider by a few centimeters every year. The Pacific Ocean is shrinking by roughly the same amount. 50 million years from now, Africa will have collided with Europe, closing the Mediterranean Sea and raising a new mountain range. Australia will have migrated northward, perhaps colliding with Southeast Asia. The continents will have rearranged themselves into new configurations, creating a world map that would be unrecognizable to us. Yet all of this will happen so slowly, so gradually, that no human will ever witness it. The changes accumulate grain by grain, millimeter by millimeter, year by year, invisible to us but inexorable. This is perhaps the most soothing aspect of plate tectonics. The reminder that change, even dramatic change, can happen through patient, gentle accumulation over vast periods of time. Mountains don't need to be thrust up in violent cataclysms. They can be raised slowly, peacefully, over millions of years, rising so gradually that you could never see them grow, yet becoming magnificent nonetheless. The three types of plate boundaries. The edges where tectonic plates meet are called plate boundaries, and they're where most of Earth's geological action occurs. There are three main types of plate boundaries, each with its own characteristic features and processes. Understanding these boundaries helps us appreciate the diversity of ways that plates interact and shape our planet's surface. Let's start with divergent boundaries, where plates are moving apart. These are perhaps the most peaceful of the three boundary types, characterized more by creation than destruction. The most prominent examples of divergent boundaries are the mid-ocean ridges we discussed earlier. At these underwater mountain ranges, two plates are slowly pulling away from each other, and hot mantle rock rises to fill the gap between them. As this mantle rock rises, the pressure on it decreases. This drop in pressure causes the rock to partially melt, even though its temperature hasn't changed. It's similar to how water boils at lower temperatures at high altitude, where air pressure is lower. The melting produces magma, which rises through cracks and fissures to erupt onto the ocean floor. These eruptions are generally gentle, with lava oozing out rather than exploding violently. The lava cools rapidly in contact with the cold ocean water, forming new oceanic crust. This new crust is initially quite hot and sits high on the ocean floor. As it moves away from the ridge, it gradually cools and contracts, becoming denser and sinking lower. This is why the ocean floor gets deeper as you move away from mid-ocean ridges. The youngest, hottest crust sits high at the ridge crest, while older, cooler crust sinks into deeper water farther from the ridge. The spreading rate at mid-ocean ridges varies considerably. The Mid-Atlantic Ridge, for example, is a slow-spreading ridge, with the plates moving apart at about 2 to 3 centimeters per year. That's roughly the rate at which your fingernails grow. The East Pacific Rise, on the other hand, is a fast-spreading ridge, with rates reaching 15 to 20 centimeters per year in some places. These differences in spreading rate affect the shape of the ridge. Slow-spreading ridges tend to have deep central valleys and rugged topography, while fast-spreading ridges have gentler slopes and shallower or absent central valleys. Not all divergent boundaries are underwater. In East Africa, a divergent boundary is splitting the continent apart, forming what's known as the East African Rift. This is a place where you can actually see a continent in the early stages of breaking apart. The rift is marked by a series of valleys and volcanic mountains, including Mount Kilimanjaro and Mount Kenya. If the rifting continues, and geological evidence suggests it will, then millions of years from now, East Africa will split completely, creating a new ocean basin between the pieces. The East African Rift is moving at only a few millimeters per year, an imperceptibly slow pace, yet over millions of years, this tiny motion will transform the geography of an entire continent. It's a reminder that dramatic geological changes don't require dramatic, violent processes. Patient, gentle forces acting over sufficient time can reshape the world. Now let's consider convergent boundaries, where plates are moving toward each other. These boundaries are more varied and complex than divergent boundaries because different types of crust can converge in different combinations. When two oceanic plates converge, one will typically be subducted beneath the other. The subducted plate bends and descends into the mantle, creating a deep ocean trench. As the plate descends, it carries water and sediments down with it. At depths of about 100 kilometers, the increasing temperature and pressure cause water to be released from minerals in the descending plate. This water rises into the overlying mantle wedge, lowering the melting point of the mantle rock and causing it to melt. The resulting magma rises toward the surface and erupts, forming a chain of volcanic islands parallel to the trench. These are called volcanic island arcs. The Aleutian Islands, the Mariana Islands, and the islands of Japan are all examples of volcanic island arcs formed by ocean-ocean convergence. The Mariana Trench, the deepest place on Earth at nearly 11 kilometers deep, was formed by this type of convergent boundary. When an oceanic plate converges with a continental plate, the denser oceanic plate is subducted beneath the more buoyant continental plate. This creates similar features to ocean-ocean convergence, a deep ocean trench and volcanic activity. However, in this case, the volcanoes form on the edge of the continent rather than as an island arc. The Andes Mountains in South America are a classic example of this type of boundary. The Nazca Plate, a piece of oceanic lithosphere, is being subducted beneath the South American plate, creating the Peru-Chile Trench and fueling the volcanic activity that has built the Andes. The subduction process also creates earthquakes. As the oceanic plate descends, it doesn't slide smoothly. Instead, it sticks and binds against the overlying plate, building up stress. Periodically, the stress becomes too great, and the plates suddenly slip, releasing energy as an earthquake. These subduction zone earthquakes can be extraordinarily powerful. The largest earthquake ever recorded, the 1960 Chile earthquake with a magnitude of 9.5, occurred at the boundary where the Nazca Plate subducts beneath South America. The third type of convergent boundary occurs when two continental plates collide. Continental crust is less dense than oceanic crust and resists subduction. When two continents collide, neither is subducted. Instead, the continental crust crumples, folds, and thickens, pushing up enormous mountain ranges. The most spectacular example of this is the Himalayan mountains, formed by the ongoing collision between the Indian and Eurasian plates. We'll explore this collision in detail later, but for now, it's enough to know that these towering peaks are the result of two continents slowly pushing into each other over millions of years. The third and final type of plate boundary is the transform boundary, where plates slide horizontally past each other. Transform boundaries don't create or destroy crust. They simply accommodate the motion between plates. The most famous example is the San Andreas Fault in California, where the Pacific Plate slides northwestward past the North American Plate at a rate of about 5 centimeters per year. Transform boundaries are characterized by earthquakes but not volcanic activity. As the plates grind past each other, they don't move smoothly. Instead, they lock together, building up stress over decades or centuries, then suddenly slip in an earthquake. The 1906 San Francisco earthquake, one of the most devastating in American history, was caused by sudden movement along the San Andreas Fault. Most transform boundaries are found on the ocean floor, connecting offset segments of mid-ocean ridges. These oceanic transform faults accommodate the different spreading rates and directions of adjacent ridge segments. On land, transform boundaries are rarer, but they can be just as significant. The Alpine Fault in New Zealand and the Dead Sea Transform in the Middle East are other examples of major transform boundaries. Each type of plate boundary creates its own characteristic landscape and geological features. Divergent boundaries create rift valleys and mid-ocean ridges, gentle features marked by volcanic activity but relatively few earthquakes. Convergent boundaries create the most dramatic features: deep ocean trenches, volcanic mountain ranges, and the world's highest peaks where continents collide. Transform boundaries create linear valleys and offset features, marked by earthquakes but not by volcanism. What's remarkable is that all these different types of boundaries are part of a single, integrated system. The Earth's tectonic plates are all interconnected, like pieces of a spherical jigsaw puzzle. A plate can't move in one place without affecting other plates elsewhere. The spreading at mid-ocean ridges is balanced by subduction at trenches. Transform faults accommodate the different speeds and directions of adjacent plates. It's all one vast, slow-moving system, with each part affecting and being affected by all the others. This interconnectedness means that events in one part of the world can have consequences thousands of kilometers away. When India collided with Asia, for example, it didn't just create the Himalayas. The collision also caused compression and faulting throughout much of Asia, affecting regions as far away as Siberia and Southeast Asia. When the Atlantic Ocean began opening up 200 million years ago, it affected plate motions all around the globe. Yet despite this global interconnectedness, the movements remain slow and gentle. Plates slide past each other at rates measured in centimeters per year. Mountains rise by millimeters annually. Ocean floors spread at the pace of growing fingernails. The system is constantly in motion, constantly changing, but it does so with infinite patience, making changes so gradual that they're invisible to human perception. This is perhaps one of the most calming aspects of plate tectonics. Our planet is not static and unchanging, but neither is it chaotic and unpredictable. It follows regular patterns, driven by consistent forces, moving at steady rates that have persisted for billions of years. The continents drift, mountains rise and erode, ocean basins open and close, all in a slow, patient rhythm that has been the heartbeat of our planet for eons and will continue for eons more. Mid-ocean ridges, the planet's longest mountain range. Deep beneath the waves, hidden from view in the perpetual darkness of the ocean depths, lies the longest mountain range on Earth. The mid-ocean ridge system winds through all the world's oceans like an enormous seam, extending for more than 65,000 kilometers. If you could drain the oceans and look down at Earth from space, you'd see this massive mountain chain snaking across the ocean floor, dwarfing any mountain range on land. The mid-ocean ridges were unknown to science until the mid-20th century. Before the development of sonar and other technologies for mapping the ocean floor, scientists assumed the deep ocean was relatively flat and featureless. The discovery of these vast submarine mountain ranges was one of the great revelations of oceanography, fundamentally changing our understanding of Earth's geology. Let's take a journey along one segment of this system, the Mid-Atlantic Ridge, which runs down the center of the Atlantic Ocean from the Arctic Ocean to the Southern Ocean near Antarctica. If you could descend to the ocean floor in a submersible, you'd find yourself in a landscape as dramatic as any on land. The ridge rises several kilometers above the surrounding abyssal plain, its slopes covered with fresh black volcanic rock. At the crest of the ridge, you'd encounter the Rift Valley, a deep crack running along the ridge's spine. This is where the North American and Eurasian plates are pulling apart in the north, and the South American and African plates are separating in the south. The Rift Valley is typically 20 to 30 kilometers wide and 1 to 3 kilometers deep, bounded by steep cliff faces. Within this Rift Valley, volcanic activity occurs regularly, though most eruptions happen without anyone knowing. The eruptions aren't like the explosive volcanic events you might see on land. Instead, lava oozes out of cracks and fissures in the ocean floor, forming pillow-shaped blobs as it's instantly chilled by the cold seawater. These pillow lavas are diagnostic of underwater volcanic eruptions, and they cover vast areas of the ocean floor. The volcanic activity at mid-ocean ridges is driven by the same process that drives all seafloor spreading: mantle rock rising to fill the gap as plates pull apart. As this hot rock rises and the pressure on it decreases, it partially melts. The resulting magma is less dense than the surrounding rock, so it rises further, eventually erupting onto the ocean floor. This process creates new oceanic crust at a rate of a few centimeters per year, adding new rock to the edges of the separating plates. Not all mid-ocean ridges spread at the same rate. The Mid-Atlantic Ridge is a slow-spreading ridge, with the plates moving apart at about 2 to 3 centimeters per year, roughly the rate at which your fingernails grow. This slow spreading produces a ridge with steep slopes and a prominent rift valley. In contrast, the East Pacific Rise, which runs up the eastern side of the Pacific Ocean, is a fast-spreading ridge with rates reaching 15 to 20 centimeters per year in some places. Fast-spreading ridges have gentler slopes, and the Rift Valley is often shallow or absent because the high rate of volcanic activity fills it in as quickly as it forms. These different spreading rates affect not just the shape of the ridge but also the characteristics of the oceanic crust that forms there. At slow-spreading ridges, the magma supply is limited, and the crust tends to be thinner and more fractured. At fast-spreading ridges, abundant magma creates thicker, smoother crust. Despite these differences, the basic process is the same. Plates pulling apart, mantle rock rising, partial melting, and volcanic eruption creating new seafloor. One of the most fascinating features of mid-ocean ridges is the hydrothermal vent systems that form where seawater circulates through cracks in the hot volcanic rock. Cold seawater seeps down through fissures in the ocean floor, is heated by contact with hot rock or magma, becomes chemically altered as it reacts with the rock, and then rises back up and vents into the ocean at temperatures that can exceed 350 degrees Celsius. These hydrothermal vents support extraordinary ecosystems unlike any found elsewhere on Earth. In the total darkness of the deep ocean, far from any sunlight, life thrives around these vents, powered not by photosynthesis but by chemosynthesis. Bacteria at the base of the food chain derive energy from the chemicals in the vent fluids, particularly hydrogen sulfide. These bacteria support a diverse community of animals, including giant tube worms that can grow several meters long, clams, mussels, crabs, and specialized fish. When hydrothermal vents were first discovered in the late 1970s, they revolutionized our understanding of the limits of life on Earth. A scientific expedition using the deep-sea submersible Alvin was exploring the Galapagos Rift when they encountered something completely unexpected. Communities of strange animals thriving in the complete darkness of the deep ocean floor, clustered around vents spewing superheated water. Scientists had assumed that all ecosystems ultimately depended on energy from the sun, either directly through photosynthesis or indirectly by consuming organisms that photosynthesize or feeding on detritus that drifted down from the sunlit surface waters. The deep ocean floor was thought to be a cold, dark desert, sparsely populated by animals eking out a living on the thin rain of organic matter falling from above. The vent communities proved this assumption spectacularly wrong. Here, in the complete absence of sunlight, at crushing pressures and near boiling temperatures, life not only survived but thrived. The base of the food chain wasn't photosynthetic algae but chemosynthetic bacteria that derived energy from hydrogen sulfide and other chemicals in the vent fluids. These bacteria, in turn, supported a remarkable diversity of animals found nowhere else on Earth. The most iconic vent organism is probably the giant tube worm, Riftia pachyptila. These creatures can grow to lengths of 2 meters or more, living in white tubes clustered around vents. They have no mouth, no digestive system, no way to eat in the conventional sense. Instead, they harbor chemosynthetic bacteria in a specialized organ called a trophosome. The tube worm absorbs hydrogen sulfide from the vent water and oxygen from seawater, delivers both to the bacteria in its trophosome, and the bacteria use the chemical energy to produce organic compounds that nourish the worm. It's a symbiotic relationship, a partnership between two very different organisms that allows both to thrive in an environment that would kill most forms of life. Other vent organisms include giant clams and mussels, some as large as dinner plates, that also host chemosynthetic bacteria. There are white crabs and shrimp, some of which farm bacteria on their bodies or in their mouths. There are fish and octopuses that feed on the vent organisms. There's even a species of snail that incorporates iron sulfide minerals into its shell, giving it a metallic appearance and earning it the nickname scalyfoot gastropod, or iron snail. These vent communities exist in a world that seems utterly alien, yet they're right here on Earth in the deep ocean. They represent an entire biosphere independent of the sun, powered instead by Earth's internal heat. This discovery has profound implications for the possibility of life on other worlds. If life can thrive around hydrothermal vents on Earth, might similar life exist around vents in the subsurface oceans thought to exist on Jupiter's moon Europa, or Saturn's moon Enceladus, or other icy worlds in our solar system? These moons have no sunlight to speak of, but they likely have liquid water and geological activity that could create hydrothermal vents. The discovery of vent communities on Earth opened up the possibility that life might be far more widespread in the universe than we previously imagined. The vents themselves are ephemeral on geological timescales. As the seafloor moves away from the spreading ridge, the vents cool and become inactive. New vents form at the ridge axis as new crust is created. Individual vents might persist for years or decades before dying out, and vent communities must continuously colonize new vents to survive as a species. How vent organisms find new vents, how their larvae disperse across vast reaches of ocean floor, and how they've evolved their remarkable adaptations to vent environments are questions that scientists are still working to answer. The black smokers and white smokers you might have seen in documentaries are types of hydrothermal vents. Black smokers emit dark clouds of mineral-rich water, the black color coming from metal sulfides precipitating out as the hot vent fluid mixes with cold seawater. White smokers emit lighter-colored fluids rich in barium, calcium, and silicon. Around these vents, minerals precipitate out of the water and gradually build up chimney structures that can reach heights of tens of meters. The mid-ocean ridge system is also where oceanic crust is youngest and hottest. As new crust forms at the ridge and then moves away, it gradually cools and contracts, becoming denser and sinking lower. This is why the ocean floor slopes downward away from mid-ocean ridges. The ridge crest sits high, sometimes as little as 2 kilometers below the ocean surface, while the abyssal plains far from the ridge lie 4 to 6 kilometers deep. This process of cooling and subsidence is remarkably regular and predictable. The depth of the ocean floor increases proportionally to the square root of its age. By measuring the depth of the ocean floor and knowing the spreading rate, scientists can calculate the age of oceanic crust quite accurately. This relationship, discovered in the 1970s, provided further confirmation of the seafloor spreading theory. In some places, mid-ocean ridges rise above sea level, creating islands where we can observe the process of seafloor spreading on dry land. Iceland is the most famous example. This island nation sits astride the mid-Atlantic ridge, where the North American and Eurasian plates are pulling apart. Iceland is essentially a piece of the mid-ocean ridge that's been elevated above sea level, probably due to an underlying mantle plume that provides extra heat and magma. In Iceland, you can literally see the plates pulling apart. The island is being split down the middle, with its western half moving westward with North America and its eastern half moving eastward with Eurasia. The Rift Valley runs right through the island, creating a series of volcanic fissures, geothermal areas, and lava fields. The rate of spreading is about 2 centimeters per year, so in a human lifetime, Iceland will widen by about 1.5 meters, a change too gradual to notice but nonetheless real and ongoing. The mid-ocean ridge system represents one of the most important geological features on our planet, yet it remains largely unexplored. We have better maps of the surface of Mars than we do of most of the ocean floor. The ridges lie in the deep ocean, difficult and expensive to reach, and most of their length has never been directly observed by human eyes. Much of what we know comes from sonar mapping, seismic studies, and data from a relatively few submersible dives and robotic vehicle surveys. Yet, even without complete exploration, we understand the basic processes at work. Plates pull apart, mantle rock rises, magma forms and erupts, new crust is created, and the ocean floor slowly spreads. This process has been occurring for at least 3 billion years, perhaps longer, constantly renewing the ocean floor in an endless cycle. Every piece of oceanic crust now on Earth's surface formed at a mid-ocean ridge within the last 200 million years. Older oceanic crust has been subducted and recycled back into the mantle. This constant renewal means that the ocean floor is young compared to the continents. While continental rocks can be billions of years old, the oldest oceanic crust is only about 200 million years old, and most of it is much younger than that. The average age of oceanic crust is about 60 to 90 million years. In geological terms, the ocean floor is fresh, new, recently formed. The mid-ocean ridges operate on a timescale so vast that their constancy is almost meditative. Year after year, century after century, millennium after millennium, the ridges slowly spread, new crust forms, and the ocean basins gradually evolve. The Atlantic Ocean has been widening for about 180 million years, and it continues to widen at the same steady rate it always has. Nothing about this process is rushed. Nothing is sudden or violent. It's patient, regular, inexorable, a slow rhythm that has persisted for eons and will continue for eons to come. The Ring of Fire, where plates collide. If mid-ocean ridges are where plates pull apart and new crust forms, then subduction zones are where plates converge and old crust is destroyed. And nowhere is this more evident than around the Pacific Ocean, where a nearly continuous chain of subduction zones forms what's known as the Ring of Fire, a zone of intense volcanic and seismic activity that encircles the Pacific Basin. The Ring of Fire is not a single feature, but rather a collection of subduction zones, volcanic arcs, and related tectonic features that together form a rough ring around the Pacific Ocean. Starting in New Zealand and heading north, the Ring of Fire includes the volcanic zones of New Zealand, the island arcs of the Western Pacific including Japan, the Philippines, and Indonesia, the Aleutian Islands, the volcanic mountains of the Pacific Northwest, the Cascade Range, and extending south through Central and South America along the Andes. This ring is home to about 75% of the world's active volcanoes and is responsible for about 90% of the world's earthquakes. The reason for all this activity is that the Pacific Plate and several smaller plates in the Pacific Basin are being subducted beneath the surrounding continental and oceanic plates. The Pacific Plate itself is the largest tectonic plate on Earth, covering about 103 million square kilometers. It's an entirely oceanic plate, containing no continents, and it's moving northwest at a rate of about 8 to 9 centimeters per year. As it moves, its edges collide with and slide beneath other plates, creating subduction zones all around its perimeter. Let's explore what happens at a subduction zone. Imagine the Pacific Plate moving northwest toward Japan. The Pacific Plate consists of old, cold, dense oceanic lithosphere, while Japan sits on the edge of the Eurasian Plate. As these plates converge, the denser Pacific Plate bends and descends beneath the Eurasian Plate, creating the Japan Trench, a deep depression in the ocean floor that reaches depths of about 8,000 meters. As the Pacific Plate descends into the mantle, it doesn't slide smoothly. The boundary between the two plates is not slippery but rather rough and irregular. The plates stick and bind against each other, and stress builds up over years or decades. Periodically, the stress becomes too great, and the plates suddenly slip, releasing energy as an earthquake. The 2011 Tohoku earthquake, which triggered a devastating tsunami and the Fukushima nuclear disaster, was caused by this kind of sudden movement at the Japan Trench subduction zone. The earthquake had a magnitude of 9.1 and released more energy than all the explosives used in World War II. As the subducting plate continues its descent, it carries with it water and hydrated minerals. At depths of about 100 kilometers, the increasing temperature and pressure cause these hydrated minerals to break down, releasing water into the overlying mantle wedge. This water has a profound effect on the mantle rock. Pure mantle rock needs temperatures of about 1200 degrees Celsius to melt, but the addition of water lowers the melting point significantly, causing the mantle rock to partially melt even at lower temperatures. This partial melting produces magma that's less dense than the surrounding rock. The magma rises through the overlying plate, eventually reaching the surface and erupting. This is the origin of the volcanic activity associated with subduction zones. The volcanoes don't form right at the trench. Instead, they form on the overriding plate, typically about 100 to 200 kilometers from the trench, at the location above where the subducting plate reaches the depth where water is released. In the case of Japan, this process has created a chain of volcanic mountains parallel to the Japan Trench. Mount Fuji, Japan's highest and most famous peak, is one of these volcanoes, formed by magma generated from the subduction of the Pacific Plate. The same process operates all around the Ring of Fire, creating volcanic arcs wherever oceanic plates are being subducted. The volcanoes of the Ring of Fire are different from those at mid-ocean ridges. Ridge volcanism involves relatively fluid basaltic lava that flows easily and erupts gently. Subduction zone volcanism involves more viscous, silica-rich magma that erupts more explosively. These are the volcanoes that produce towering ash clouds, pyroclastic flows, and catastrophic eruptions. Mount St. Helens, Krakatoa, Mount Pinatubo, and Nevado del Ruiz are all subduction zone volcanoes that have produced devastating eruptions in recent history. Yet, even the most violent volcanic eruption is just a brief punctuation in the slow, patient process of subduction. The plates continue their steady convergence whether volcanoes are erupting or not. The Pacific Plate descends into the mantle at a rate of about 8 centimeters per year. Every year, decade after decade, millennium after millennium. Over millions of years, thousands of kilometers of oceanic crust have been subducted beneath Japan, beneath South America, beneath the other boundaries around the Pacific. Moving south from Japan along the Ring of Fire, we encounter the Philippine Sea Plate being subducted beneath the Eurasian Plate, creating the Philippine Trench and fueling the volcanic activity in the Philippines. Further south, the complex interactions between the Pacific, Australian, and smaller plates create the incredibly active volcanic zones of Indonesia. This region has more active volcanoes than anywhere else on Earth, and it's also one of the most seismically active regions. The 2004 Indian Ocean earthquake and tsunami, one of the deadliest natural disasters in recorded history, occurred at a subduction zone off the coast of Sumatra, where the Indo-Australian Plate is subducting beneath the Eurasian Plate. The earthquake had a magnitude of 9.1 to 9.3 and caused a tsunami that killed more than 230,000 people in 14 countries around the Indian Ocean rim. The earthquake itself lasted between 8 and 10 minutes, an extraordinarily long duration that indicates just how much of the fault ruptured simultaneously. The rupture extended for about 1,500 kilometers along the subduction zone, one of the longest earthquake ruptures ever recorded. The amount of energy released by this earthquake was staggering. It's estimated that the earthquake released energy equivalent to about 23,000 atomic bombs of the size dropped on Hiroshima, or about 9.5 times 10 to the 18th joules. This energy had been accumulating in the rocks at the plate boundary for centuries as the Indo-Australian Plate slowly pushed beneath the Eurasian Plate, bending and stressing the rocks at the interface. When the stress finally exceeded the strength of the rock, the fault suddenly slipped, with the seafloor jumping upward by several meters along the entire length of the rupture. This sudden vertical displacement of the seafloor displaced an enormous volume of water, creating the tsunami that devastated coastlines throughout the Indian Ocean. The waves reached heights of up to 30 meters in some locations and traveled across the entire Indian Ocean basin, reaching the coast of Africa thousands of kilometers away. The tsunami killed people in Indonesia, Thailand, Sri Lanka, India, and even in Somalia and Kenya. It was a stark reminder that plate tectonic processes, while slow on human timescales, can release energy catastrophically when accumulated stress is suddenly released. Heading eastward across the northern Pacific, we come to the Aleutian Islands, a chain of volcanic islands formed by the subduction of the Pacific Plate beneath the North American Plate. The Aleutian Trench marks the boundary between these plates, and the Aleutian Islands are the volcanic arc resulting from this subduction. The islands curve across the northern Pacific in a graceful arc, each island representing a volcano built by magma from the subducting Pacific Plate. Continuing southeast, the subduction zone extends along the Pacific coast of North America, creating the Cascade Range, a chain of volcanic mountains that includes Mount Rainier, Mount Hood, Mount Shasta, and others. These mountains are the result of the Juan de Fuca Plate, a small oceanic plate, subducting beneath the North American Plate. The Cascadia subduction zone, as it's called, is capable of producing massive earthquakes, though it doesn't do so frequently. The last major earthquake on this subduction zone occurred in 1700, and geological evidence suggests that such earthquakes occur every few hundred years on average. Further south, the Ring of Fire continues through Central America and South America, where the Cocos and Nazca plates are subducting beneath the Caribbean and South American plates. This subduction has created the volcanic mountains of Central America and the Andes, the longest continental mountain range in the world. The Andes stretch for about 7,000 kilometers along the western edge of South America, paralleling the Peru-Chile Trench where the Nazca Plate is being subducted. The Andes are still rising. The ongoing subduction means that the Andes continue to be uplifted, though the process is partially offset by erosion. Some of the highest peaks in the Andes are active or recently active volcanoes, fed by magma from the subducting Nazca Plate. The region experiences frequent earthquakes as stress builds and releases along the subduction zone. What's striking about the Ring of Fire is both the violence of individual events and the patience of the overall process. Earthquakes and volcanic eruptions can be catastrophic, releasing in seconds or minutes energy that has been accumulating for decades or centuries. Yet these dramatic events are just moments in a process that has been ongoing for tens of millions of years and will continue for tens of millions more. The Pacific Plate has been subducting beneath surrounding plates for at least 100 million years. During that time, thousands of volcanoes have erupted, millions of earthquakes have occurred, and an area of oceanic crust roughly the size of several continents has been consumed and recycled into the mantle. Yet the process continues at the same steady rate, driven by the same convective forces in the mantle that have been operating for billions of years. There's something almost meditative about contemplating the Ring of Fire on geological timescales. From our human perspective, earthquakes and eruptions seem sudden and unpredictable. But on the timescale of plate tectonics, they're regular, expected events, the natural consequence of plates converging at steady rates. The stress builds gradually, predictably, and eventually it must be released. The cycle repeats endlessly year after year, century after century. The Ring of Fire also reminds us that plate tectonics isn't just an abstract scientific theory but a process with profound effects on human societies. The same tectonic processes that build mountains and shape ocean basins also create hazards for the millions of people who live in tectonically active zones. Understanding plate tectonics helps us understand these hazards and prepare for them, though we can never eliminate the risks entirely. As long as the plates continue to move, and they will continue for billions of years, earthquakes and eruptions will occur. Yet even in the most active parts of the Ring of Fire, the underlying process remains slow and steady. The plates converge at rates of a few centimeters per year. Mountains rise by millimeters annually. Volcanoes erupt occasionally, but spend most of their time quietly dormant. The Earth is constantly reshaping itself, but it does so patiently, over timescales that dwarf human lifetimes. The majestic Himalayan collision. Of all the consequences of plate tectonics, perhaps none is more visually dramatic than the Himalayan mountains. These towering peaks, including Mount Everest, the highest point on Earth at 8,849 meters above sea level, are the result of one of the most significant tectonic events currently occurring on our planet: the ongoing collision between the Indian and Eurasian plates. To understand this collision, we need to journey back in time to when India was not attached to Asia at all. 140 million years ago, during the age of dinosaurs, India was part of the southern supercontinent of Gondwana, joined with Antarctica, Australia, Africa, and South America. At that time, a vast ocean called the Tethys Sea separated Gondwana from the northern continents. Around 120 million years ago, India began to separate from Gondwana, rifting away from what is now Antarctica and Madagascar. A mid-ocean ridge formed between India and Antarctica, and seafloor spreading began pushing India northward across the Tethys Ocean toward Asia. This northward journey wasn't a straight line, but rather a complex path influenced by other tectonic movements and the rotation of the plate. What's remarkable is the speed at which India moved during this period. In plate tectonic terms, India was racing northward at rates of up to 15 to 20 centimeters per year, exceptionally fast for continental drift. This rapid movement was driven by strong mantle convection beneath the Indian plate, pulling it away from Antarctica and pushing it toward Asia. As India moved north, it carried with it a cargo of unique plants and animals that had evolved in isolation on Gondwana. When India eventually collided with Asia, these Gondwanan species mixed with Asian species, creating the biodiversity hotspot that is the Indian subcontinent today. But that collision was still millions of years in the future. For tens of millions of years, India was an island continent, slowly crossing the Tethys Ocean. The ocean floor in front of India was being subducted beneath the Eurasian plate, consumed in a subduction zone along the southern edge of Asia. This subduction created a volcanic arc along southern Asia and a deep ocean trench where the oceanic crust descended into the mantle. Around 50 to 55 million years ago, India's northward journey brought it into contact with Asia. The exact timing is debated among geologists, but the general sequence of events is well understood. When India first touched Asia, there was still oceanic crust between them, and this continued to be subducted. But gradually, as India pushed farther north, the ocean basin closed completely, and the two continental masses came into direct contact. This is when things got interesting. Continental crust is less dense than oceanic crust and resists subduction. When two continents collide, neither wants to sink into the mantle. Instead, the crust crumples, folds, and thickens. It's like pushing two pieces of thick cardboard together. They buckle and pile up rather than sliding smoothly past each other. The collision between India and Asia pushed up the Himalayan mountains, the Tibetan Plateau, and affected tectonics across much of Asia. The process of forming these mountains involved several different mechanisms working together. The crust didn't simply pile up uniformly. Instead, it deformed in complex ways. Some parts of the crust were thrust up along fault lines, with older rocks being pushed up and over younger rocks in massive overthrust sheets. These thrust faults can move rock hundreds of kilometers horizontally and lift it several kilometers vertically. The main central thrust and the main boundary thrust are two major fault systems in the Himalayas that have accommodated much of the collision's motion, lifting ancient metamorphic rocks from deep in the crust and exposing them at the surface. Other parts of the crust were folded like rumpled fabric. When you push on the edges of a tablecloth, it doesn't simply compress uniformly. Instead, it buckles and folds. The same thing happened to the rock layers in the Himalayas. Rocks that were once flat-lying sedimentary beds deposited in the Tethys Ocean have been folded into spectacular shapes, with layers bent into arcs, loops, and complex three-dimensional geometries. The crust also thickened enormously in the collision zone. Normal continental crust is 30 to 40 kilometers thick, but beneath the Himalayas and especially beneath the Tibetan Plateau, the crust reaches thicknesses of 70 to 80 kilometers. This is nearly double the normal thickness, achieved by crushing and stacking crustal rocks on top of each other. It's like closing a thick book. The pages don't disappear, they just take up less horizontal space and more vertical space. The Himalayas themselves are made of rocks that once formed the floor of the Tethys Ocean and the sediments that accumulated in that ocean over millions of years. These marine rocks, complete with fossils of ancient sea creatures, have been thrust up to become the highest mountains on Earth. Near the summit of Mount Everest, climbers encounter limestone formations containing fossils of marine organisms that lived in shallow tropical seas 50 million years ago. These fossils include crinoids, sea lilies, brachiopods, lampshells, and trilobites, all creatures that lived on or near the ocean floor. To think that the highest point on Earth was once an ocean floor is almost dizzying, a reminder of how dramatically plate tectonics can transform landscapes. The summit of Everest is known to geologists as the Yellow Band, a layer of yellow-brown limestone rich in these marine fossils. Above the yellow band are rocks from even deeper in the Earth's crust, metamorphic rocks that were subjected to tremendous heat and pressure deep underground before being thrust upward by the collision. These include schist, gneiss, and marble, rocks whose original textures and mineral compositions have been completely transformed by their journey through the deep crust. The collision didn't happen all at once. It's been an ongoing process for 50 million years and continues today. India is still pushing northward into Asia at a rate of about 5 centimeters per year. This ongoing collision has several consequences. First, it continues to uplift the Himalayas. The mountains are still rising, gaining about 5 millimeters in height each year on average, though this is partially offset by erosion. Second, the collision has created the Tibetan Plateau, a vast, elevated region north of the Himalayas that's often called the roof of the world. The plateau averages about 4,500 meters in elevation and covers an area of about 2.5 million square kilometers. It formed as the collision between India and Asia compressed and thickened the continental crust in this region, pushing it upward. Third, the collision has affected tectonics throughout Asia. The force of India pushing into Asia has to go somewhere, and it's caused faulting, mountain building, and earthquakes across a vast region. The ongoing collision is responsible for the high seismicity of the Himalayan region and much of Central and Eastern Asia. The Himalayas contain 14 peaks over 8,000 meters in height, known to mountaineers as the 8,000ers. These include Mount Everest, K2, Kangchenjunga, Lhotse, Makalu, and others. Each of these mountains is a monument to the power of plate tectonics, built grain by grain, millimeter by millimeter, over millions of years by the slow but inexorable collision of two continents. What's particularly calming about the Himalayan collision is its timescale. These mountains, among the most dramatic and imposing on Earth, didn't spring up overnight in some catastrophic event. They've been rising slowly, steadily, for 50 million years. If you could somehow watch a time-lapse of the Himalayas forming, with each second representing 10,000 years, it would still take more than 83 minutes to watch them rise from sea level to their current height. Even today, with the mountains fully formed, they continue to rise at just 5 millimeters per year. In a human lifetime of 80 years, the Himalayas will rise by just 40 centimeters. You could spend your entire life in the shadow of Everest and never perceive its growth. Yet it's happening nonetheless, patient and unstoppable, millimeter by millimeter, year after year. The Himalayas also illustrate the interplay between tectonic uplift and erosion. While the collision between India and Asia pushes the mountains upward, erosion constantly wears them down. Rivers carve deep gorges through the mountains, carrying sediment down to the lowlands and eventually to the ocean. The monsoon rains that drench the southern slopes of the Himalayas each year accelerate this erosion, stripping away rock and soil. Yet despite this erosion, the mountains continue to rise because the rate of uplift exceeds the rate of erosion. The balance between these two processes determines the height and shape of mountain ranges. If uplift stops, erosion will eventually level any mountain range, given enough time. But as long as the collision between India and Asia continues, the Himalayas will continue to rise. Geologists predict that this collision will continue for many millions of years into the future. India is still moving north at 5 centimeters per year, and there's no sign of this motion stopping. Eventually, perhaps in another 20 or 30 million years, India may be fully absorbed into Asia, and the collision will cease. At that point, erosion will begin to dominate, and the Himalayas will gradually be worn down. But that's millions of years in the future. For now, and for the foreseeable geological future, the Himalayas will continue their slow, steady rise. The Himalayan collision also has global effects. The uplift of the Himalayas and the Tibetan Plateau has influenced global climate patterns. The high mountains affect the Asian monsoon system, which brings rain to billions of people. The weathering of Himalayan rocks consumes carbon dioxide from the atmosphere, potentially affecting global climate over millions of years. The erosion of the Himalayas provides sediment to some of the world's greatest rivers, including the Ganges, Brahmaputra, Indus, and Yangtze, which support vast agricultural regions and some of the highest population densities on Earth. All of this complexity, all of these far-reaching effects, stem from something as simple as two plates moving toward each other at 5 centimeters per year. It's a reminder that small, steady processes, given enough time, can have effects that dwarf anything humans can achieve. We can't build mountains like the Himalayas, but the patient, gentle force of plate tectonics can, simply by maintaining a steady pressure for millions of years. The slow, steady rhythm of plate movement. One of the most soothing aspects of plate tectonics is its predictability and constancy. Unlike many geological processes that can vary dramatically in rate or stop and start unpredictably, plate motions are remarkably steady over millions of years. This constancy provides a rhythmic quality to plate tectonics, a slow, patient drumbeat that has been maintaining the same tempo for billions of years. Scientists can measure plate motion rates with remarkable precision using several techniques. One of the most important is GPS, the Global Positioning System. GPS stations can detect motion of just a few millimeters per year by precisely measuring their position relative to satellites. By placing GPS stations on different tectonic plates and monitoring their motion over years, scientists can determine exactly how fast and in what direction each plate is moving. What these measurements reveal is that plate motions are very steady. The Mid-Atlantic Ridge has been spreading at roughly 2 to 3 centimeters per year for millions of years. The Pacific Plate has been moving northwest at about 8 to 9 centimeters per year for at least several million years. The collision between India and Asia has been occurring at about 5 centimeters per year for millions of years. These rates vary slightly over time, but the variations are small. Plates don't suddenly accelerate or reverse direction. They maintain steady courses at steady speeds, driven by the patient, consistent force of mantle convection. The fastest moving plate is the Cocos Plate, a small oceanic plate off the coast of Central America, which moves at about 9 to 10 centimeters per year. The slowest major motion is at the Mid-Atlantic Ridge, where plates separate at about 2 centimeters per year. Most plate motions fall somewhere in this range, between 2 and 10 centimeters per year. To put this in perspective, your fingernails grow at about 3 centimeters per year, right in the middle of the range of plate motion rates. This means that tectonic plates move at about the same rate that your hair grows, that your fingernails extend, that a seedling grows in its first weeks. These are gentle, patient processes, invisible from day to day but producing measurable results over weeks and months. And just as your fingernails grow steadily, day after day, without you noticing or thinking about it, so too do tectonic plates move steadily, year after year, reshaping the Earth's surface. Over millions of years, these slow motions accumulate into dramatic changes. The Atlantic Ocean has been widening at about 3 centimeters per year for about 180 million years. In that time, it has grown from a narrow rift to an ocean basin 6,000 kilometers wide. South America and Africa, once pressed together as part of Pangaea, are now separated by thousands of kilometers of ocean. Yet this transformation happened at the pace of growing fingernails, no faster, no slower, just patient and steady. Geologists can reconstruct the past positions of continents by running plate motions backward in time. By knowing the current motion of plates and the age of the ocean floor, they can determine where continents were in the past. These reconstructions reveal that Earth's geography has changed dramatically over geological time. 250 million years ago, all the continents were joined in Pangaea. But Pangaea wasn't the first supercontinent. Before it, there was Rodinia, which formed about 1 billion years ago and began breaking apart around 750 million years ago. Before Rodinia, there may have been other supercontinents, though the evidence becomes harder to read as we go further back in time. The assembly and breakup of supercontinents follows a pattern known as the supercontinent cycle. Continents drift together, collide, and form a supercontinent. The supercontinent persists for some time, then begins to rift apart. The fragments drift away from each other, eventually colliding with other continental fragments to form a new supercontinent. This cycle takes about 400 to 600 million years to complete. We're currently in the dispersal phase of the cycle. Pangaea broke apart starting about 200 million years ago, and the continents have been drifting apart since then. The Atlantic and Indian Oceans have opened up, and the continents are widely scattered. But this dispersal won't continue forever. Eventually, the continents will begin drifting back together, forming a new supercontinent. Geologists have made predictions about the future geography of Earth based on current plate motions and our understanding of the forces driving those motions. In about 50 million years, Africa will continue its northward drift and collide more fully with Europe, completely closing the Mediterranean Sea and creating a mountain range comparable to the Himalayas. This future mountain range, sometimes called the Mediterranean Mountains or the Atlas Alps chain, will stretch from Spain to the Middle East, formed by the same processes that are currently building the Himalayas, continental collision, crustal thickening, thrust faulting, and folding. Australia, currently drifting northward at about 7 centimeters per year, will continue its journey towards Southeast Asia. In about 50 million years, it may collide with Indonesia and other parts of Southeast Asia, creating new mountain ranges and fundamentally altering the geography of the region. The complex island chains of Indonesia might be crushed between Australia and Asia, uplifted into mountain ranges connecting the two landmasses. The Atlantic Ocean will eventually stop widening. The mid-ocean ridge system that has been spreading the ocean floor apart for 180 million years will eventually become dormant, as happened to other ridges in Earth's past. Once the spreading stops, the old oceanic lithosphere on both sides of the ocean will begin to cool and contract, becoming denser. Eventually, it may become dense enough to sink, initiating subduction. The Atlantic could begin to close, with subduction zones forming either along its margins or perhaps down its center along the old mid-ocean ridge. Meanwhile, the Pacific Ocean will continue to shrink as the Pacific Plate is subducted beneath surrounding plates. The Ring of Fire will persist, continuing to produce earthquakes and eruptions as it has for tens of millions of years. Eventually, in the distant future, the Pacific may close entirely, bringing the Americas into contact with Asia on one side and Australia on the other. These movements will eventually lead to the formation of a new supercontinent. One scenario, called Pangaea Proxima, envisions the Americas colliding with Africa and Europe as the Atlantic closes, while Australia collides with East Asia, creating a new supercontinent that looks somewhat like Pangaea but rotated and rearranged. Another scenario, called Amasia, suggests that the Americas and Asia will drift northward and collide in the Arctic region, creating a supercontinent centered around the North Pole. Which scenario will actually occur depends on details that are difficult to predict. The exact pattern of mantle convection, the precise movements of plates, and the formation of new subduction zones all influence how continents will move in the distant future. These details are uncertain, making precise predictions impossible. But the overall pattern is clear. The continents will continue to drift, they will eventually collide again, and a new supercontinent will form, continuing the supercontinent cycle that has operated for billions of years. The supercontinent cycle itself is one of the most fundamental rhythms of our planet. Continents assemble into supercontinents, persist for some time as unified landmasses, then rift apart and disperse. The assembly phase involves the closing of ocean basins through subduction and the collision of continents. The dispersal phase involves the rifting of continents and the opening of new ocean basins through seafloor spreading. Each complete cycle takes about 400 to 600 million years. We can trace this cycle backward in time through Pangaea, which existed from about 300 to 200 million years ago, and Rodinia, which existed from about 1 billion to 750 million years ago. Before Rodinia, there was likely Columbia, also called Nuna, which existed around 1.6 to 1.3 billion years ago. Before Columbia, there may have been other supercontinents, but the evidence becomes increasingly difficult to read the farther back we go. Each supercontinent had its own unique geography, its own arrangement of land masses, its own mountain ranges and coastlines. But the process that formed each one was fundamentally the same. Continents drifting across the face of the Earth, driven by mantle convection, assembling when they collided and dispersing when they rift apart. The specifics change, but the pattern persists, a planetary rhythm that has been beating for as long as plate tectonics has operated on Earth. These predictions are speculative in the details, but the overall pattern is based on solid understanding of plate tectonics. Just as we can predict where a thrown ball will land by understanding its motion and the forces acting on it, we can predict roughly how continents will move by understanding their current motions and the forces driving them. The continents won't stop moving. They'll continue their slow drift, following the dictates of mantle convection, assembling into a new configuration over the next few 100 million years. What's remarkable is that all of this happens at rates we can barely perceive. If you could live for 1 million years, you'd see continents move about 20 to 90 kilometers, depending on which plate you were observing. That's noticeable, but it's not dramatic. The shapes of continents would look much the same. Ocean basins would be slightly wider or narrower, but not transformed. You'd need to live for tens of millions of years to see truly dramatic changes, and hundreds of millions of years to see continents collide and assemble into a supercontinent. Yet, even these vast timescales are accessible to us through geological study. By reading the rocks, by studying fossils and magnetic patterns in mountain ranges, geologists can reconstruct what the Earth looked like hundreds of millions of years ago and predict what it will look like hundreds of millions of years in the future. We can see the whole supercontinent cycle, from assembly to breakup to reassembly, even though no human will ever witness more than the tiniest fraction of that cycle. The constancy of plate motions is reassuring. In a world where so much seems chaotic and unpredictable, where climate changes and species go extinct and human societies rise and fall, plate tectonics continues its patient work, unmoved by everything happening on the surface. The plates don't know or care about ice ages or asteroid impacts or the evolution of life. They just keep moving, steady and patient, at rates determined by forces deep within the Earth. This perspective can be calming. Our individual lives are brief, our civilizations ephemeral, our species perhaps just a moment in Earth's long history. But the processes that shape our planet operate on timescales so vast that they're essentially eternal from our perspective. The plates will keep moving long after our civilization is gone, long after our species has evolved into something else or gone extinct. They were moving long before the first humans appeared, long before the first animals crawled onto land, long before life itself may have begun. And they'll keep moving until the Earth itself is gone. Perhaps 5 billion years from now, when the sun expands into a red giant and engulfs the inner planets. There's something profoundly peaceful about this perspective. We're part of something much larger and longer lasting than ourselves, part of a planet that's been reshaping itself for 4.5 billion years and will continue to do so for billions more. We get to live on this dynamic, ever-changing world for a brief moment, and we have the privilege of understanding how it works, of seeing the patterns and processes that will continue long after we're gone. Closing. As we come to the end of our journey through the peaceful world of plate tectonics, let's take a moment to reflect on what we've discovered. We've seen how continents drift across the surface of our planet at the pace of growing fingernails, how new ocean floor is born at mid-ocean ridges and old ocean floor returns to the mantle at subduction zones, how mountains rise grain by grain over millions of years, and how all of this happens in a slow, steady rhythm that has been maintained for billions of years. The theory of plate tectonics is one of the great intellectual achievements of humanity. a unifying framework that explains so much about how our planet works. It tells us that Earth is not static but dynamic, not unchanging but in constant, gentle flux. It reminds us that dramatic transformations can occur through patient, steady processes applied over vast timescales. It shows us that the ground beneath our feet, which seems so solid and permanent, is actually riding on vast plates of rock that float on a partially molten mantle, driven by heat from deep within the Earth. Perhaps most importantly for tonight's purpose, plate tectonics teaches us patience. The mountains didn't need to appear overnight. The oceans didn't need to open in catastrophic floods. The continents didn't need to race across the globe. Everything happened slowly, steadily, at rates so gentle that no single organism could ever perceive them. Yet over millions of years, these patient processes have transformed our planet again and again. As you drift off to sleep tonight, imagine yourself floating above the Earth, looking down at the continents and oceans. Know that beneath you, the plates are moving, just as they have been for billions of years. The Atlantic is getting a few centimeters wider. The Pacific is shrinking by roughly the same amount. The Himalayas are rising by a few millimeters. New ocean floor is forming at mid-ocean ridges. Old ocean floor is descending into the mantle at subduction zones. All of this is happening right now, as you rest so slowly and gently that you could never feel it, yet so surely and steadily that it will continue for millions of years to come. Let the rhythm of these ancient processes lull you into sleep. Let the patience of plate tectonics remind you that not everything needs to happen quickly. Some of the most important and dramatic changes occur through gentle, steady accumulation over time. Rest easy knowing that our planet will continue its slow dance, reshaping itself with infinite patience, long after we've drifted off into peaceful dreams. If you enjoyed learning about the gentle science of plate tectonics tonight, please consider liking this video and subscribing to Deep Science Sleep. Hit that notification bell to be notified when new sleepy science stories are released. Sweet dreams, and may the peaceful rhythm of Earth's tectonic plates carry you into the deepest, most restful sleep.